So I'm recording. So for the quiz next Monday, you can either do it through Blackboard. If that's causing you trouble, then you can send me an email. If you are in a different time zone and so can't easily do it at this time, send me an email because I can make it so that people will see the quiz starting at different times. So just in the next couple days, send me an email saying, I'm in a different time zone and give me a possible time for when you can start, and we'll deal with that. In general, if there are problems, I have to be flexible, so you'll let me know. Okay, so for the quiz, the review you got is actually pretty good. So it is on these sections. And if you remember, this looks worse than it is. It looks like it's more material than it is because 3.4 is the triple integrals. 0.5 is volume, which is the same thing. You're just integrating one instead of a function. And 3.8 is mass and density. And that's, again, just a triple integral where you are integrating a density function, which I have to give you. So really 3.4, 3.5, and 3.8 are just different things all doing triple integrals. And 3.6 introduces into it, instead of just rectangular coordinates, it introduces the cylindrical and spherical coordinates. So that's sort of the one that's new. And once that's been introduced, that can be in any other section. So in terms of volume, in terms of integrating over space, in terms of mass. So that's what the quiz will be on. So pretty much about the same length as the mock quiz, but with these sort of two additional pieces. And there's not much to that, except for the spherical. So spherical is really the only new thing that wasn't going to be on the quiz last week, but will be on the quiz next Monday. So someone asked about the midterm. So right now, I'm delaying to say when the midterm is because it'll somewhat depend on how things go on Monday. I would like to have the midterm in 2 weeks. And if the quiz with all the submissions goes well on Monday, it will be in 2 weeks. But I'll wait until Monday to ask when you have other midterms and so on to figure out when it actually is. Also, this could be the last quiz because these are kind of a pain for both of us. And if it's the last submitted one, I will still probably have a quiz like one last week where it's a mock quiz, just so you can try the material on your own to make sure you know how to do it. So any questions about quiz, just the material? So if you remember from last week, two things. One is sometimes the chat is lagging and I can't save the file, so what I'm going to have to do is erase and rewrite it. So I will usually delay between erasing. So I'm going to erase this. And we are in 2.8. So final is really, we'll find out. Final will really find out what goes on with the quiz and so on. We haven't completely decided how that's going to work yet. It's likely that at least part of it will somehow be multiple choice to make it easier for both of us for submitting and grading. And quiz is on day. So next Monday will be the actual quiz. So you tried it yesterday, hopefully, and then the actual quiz will be on Monday. So we're not going to do anything because the quiz is going to be a bit of a trial. We're not going to do anything except for the quiz on Monday. And so it'll be up on Blackboard I'll send out an announcement. It'll be up on Blackboard at something like 10:20, 10:25. Then you get an hour to both do it and then submit it. And I'll send out an announcement for that. So we got into quickly 2.8, and really I want to do this example and lead into the next section, because by itself 2.8 isn't something we care about. It's just a tool that we can use to further things. So I do the first example, a fairly easy one to remind you what we're getting here, which is you can see it's a really simple one. We're getting a vector function where there's more than one variable, and we want to check one thing here, and then there's an add-on that we didn't get to last week, which I'll put in, which is we want to check, is this regular? In the actual question, they also ask you to graph it, but things like that, as usual, you don't have to worry about. So to check if it's regular, there are three things to check, but one of them is pretty much automatic for the types of functions we get, which is we need the region we're looking at is nice. For most of the ones we look at, it's just going to be everything. So in this case, there's no value of u or v that we can plug in that isn't defined. So it's just the whole real space, and therefore that is automatically. So the first one for us almost always is automatic. The second one is we need the derivative to be nice, so we need it to be differentiable. So we take the two partial derivatives, and again, we need that to be defined and all on the space we're looking at. And again, you can see most of the time that's fairly obviously true. About the only problems is dividing by 0, taking square roots and negatives, stuff like that. And the third one is we need the two vectors to be linearly independent, and you'll see why we need that when we add in part that we didn't quite get to on Thursday. So there are two ways of doing this. The easy way is to be linearly independent, you can't have either of the vectors as a constant multiple of the other one. And here, that's pretty obvious because of the two middle ones. Obviously, 1 times anything be 0, and 0 times something being 1. So this is also pretty obviously true. So this is regular everywhere. They actually just ask you to show that it's regular at a particular point. Here it's true everywhere. So that usually is in the background for us, except for the last piece, the linear independent. That's the one thing you might show. So any questions on this? This is, as I said, mostly in the background. As I said, I'll delay because there's a lag in chat and I have to erase. Okay. All right, so I will erase and add in the little piece that we'll do, which is, so note given a parameterization like the one we just had, we have another way of getting a tangent plane at a particular point. And it should look familiar from the tangent line that we did way back in chapter 1, which is the x, y, z, the point in general, will be equal to the point at the given value u0, v0, plus the a variable, which I'll talk about in a second, times the derivative with respect to u at that point, and plus a second variable of the other partial derivative. So these, the a and b, obviously we can't use x and y, our usual variables. We could use s and t if we wanted to, but that often indicates time, so we don't really want to use that. We have u and v already, so whatever you want to call the variable. So let's look at this particular example. So back to 1. It's 1, 2. Let's check. Yes, so 1, 2. So you can see what we need is we need to know what is, if I plug 1, 2 into the original function, which unfortunately I don't have, but hopefully you have in your notes, it's problem 1. The function was the u squared plus v squared comma u comma v. So therefore this will be equal to 5, 1, and 2. We found that derivative with respect to u is 2u comma 1 comma 0. So when I plug into that, I get 210. And when I plug into the derivative with respect to v, which is 2v01, and I get 401. And I'm going to try to keep it in this one page so everything's together. That last one's supposed to be a 401. I should say, I think I forgot at the beginning, is like Thursdays, I'm also writing these notes up and putting them on Blackboard under notes. So these will also be there. So you can kind of see why we need them to be linearly independent, because if this vector was a multiple of this vector, we wouldn't be getting anything new from the second vector, so we'd be only getting one dimension, therefore we'd be getting a line. So if they're not linearly independent, it would just be giving us a line, as opposed to a three-dimensional plane. So there's the basic one. So we can get another way of doing tangent planes given this. Again, this is kind of in the background for us. So this is not why we do the parameterization. But any questions on this? Okay, so let me erase again. And again, I'll remind you this every once in a while, is if you stop hearing me, say something in chat so I to make sure and try to fix it. So let me put this down because we're going to now use them. So another way of checking to see if these two vectors are linearly independent is to look at the cross product, which seems silly, but will become useful when we go into the next section, 3.11. So Julie asks, do we leave, so sorry about erasing it. We do leave the A and B as variables, so they're like an X and a Y. It's just that we've used X and Y and so on. So yes, the final one there will be an A and a B. Those are the variables. So we're going to take cross product. And we do it in the usual way. It just looks different because now we have variables. So we do this, the memorization technique, where we do the I times. And remember what we do is, since I'm looking at the I, I'm getting rid of the first row and the first column and get what's left. For J, I'm getting rid of the row and the column it's in, so I'm getting rid of the first row and the second column. And for K, I'm getting rid of the first row and third column. Sorry about the extra line. Oh, that should be a plus. Thank you. So I get the 1 times I and 2u times j and oh, I put something wrong. That last one. Sorry, I'm not sure why it's doing that. Let me rewrite that last one again. So first. So that should have been that. So I get that. That's the cross product. And the two vectors, the two gradient vectors, do not give a cross product that's 0, 0, 0. And that tells you that they're linearly independent. Okay. So this is the second way of doing it. Obviously, the easier way is the way we did it before, which is obviously RU is not a constant multiple of RV, and we're done. So in some sense, this way of doing it is silly if all we're doing is checking to see if they're linearly independent. But we'll see that we do want to do it this way for the next section. So sorry about the mess. So any questions on this before I erase? So this leads into 3.11. We'll come back tomorrow to 1 or 2 more examples from 2.8, but I want to get to what the actual use is, because 2.8 by itself is not really anything. It's just a tool. So let's actually use it. So what we want to be able to do is we want to be able to get the area of a two-dimensional surface in 3 dimensions. So as an easy example for me to draw, because as you know, I can't draw very well in 3 dimensions. So for example, we have a paraboloid, and I want to find what is the surface area above the xy plane of that thing. So that's what we want to be able to get. We know that in integrals, what we're always trying to do is break them up into little pieces and add them up. So what you might expect is we're going to say, oh, well, what we're going to do is we're going to break up, and I can't draw this very well, as always. Break it up into lots of pieces where we can assume it's not curving or not very much, get the area of that little piece, which hopefully is fairly simple, and then add them all up. The problem is, in terms of x and y, it's not obvious how you get those pieces, but once we parameterize it, it's not too bad. So this is kind of my rough intro, sorry about that. So let me go to the next one and do what we're actually going to do. So we want to look at a three-dimensional object over some region, which might be a circle, it might be a box that u goes from 0 to 1, v goes from 0 to 1, and we want to find the surface area above that little box. For this to work, we will need R to be regular. That's supposed to be UV. We know that's at the point UV, not sure why it's doing these little loops and stuff. It's catching my finger, I guess. Sorry about that. So R, we know that at the point UV, R changes by about the partial derivative with respect to u in the u direction. And sorry about this. So in this case, I'm making R now generic, but we could do the last example, the z equals 5 minus x squared minus y squared, and parameterize it, which we'll do in a bit. So R is a function that has a two-dimensional surface in 3 dimensions. So R changes by about RV, RU, with the derivative with respect to and the derivative with respect to b. We can assume for small changes, this is about a parallel. So, oh, never mind. I just wasn't talking. Someone said I wasn't. They didn't hear. That's because I stopped talking for a minute. Okay. We know that's going to make a parallelogram. If we can assume it makes a parallelogram if we don't move very far. And now this goes back to chapter 1. So let me erase this, and I'm going to ask you a question from chapter 1. So first, any questions on this? Okay. Given a parallelogram formed by two vectors u and v, how do we get the area of the parallelogram formed by those two vectors? So it's a chapter 1 question. So someone says the magnitude of cross product. If I go back to the last one, the sides are the vectors of the two partial derivatives. So in our case, it's equal to the magnitude of the cross product of RU and RB. And then we do the usual I should really put an A and a B there, whatever the numbers are. Do the double integral over du dv, and resolve the magnitude. So you can see to get the surface area, we need the cross product. So if we're checking to see if something is regular, and we're then going to get the surface area, we might as well take the cross product and check if it's regular that way, see if they're linearly independent that way, because we're going to need it anyway. Okay, so just to show hopefully what's going on here, let me go back to the example 1 from 2.8, make this more specific. Because of the one question. So any questions on this before I erase again? So back to the question from problem 1. So we had this. Oh, someone answered the question. Sorry about that. And if you go back to the original one, the R was giving us a two-dimensional object in 3 dimensions. So the original one was R is u squared plus v squared, and then comma u, comma v. If I put in all the values of u, it would give me some kind of surface in 3 dimensions. And I'll sort of draw this in a second. Actually, I might as well just do it now, which is, let me pretend surface looks like that. That's supposed to be curving and so on. But so if I'm at the point of, I forget what we hear, 1, 2. So if I plug in u equals 1 and v equals 2, I got the 5, I forget what the numbers are, 5, 2, 1. So there it is. And then I'm going to get 2 vectors representing the partial derivative with respect to u and the partial derivative with respect to v, which in this case are the 2, 1, 0 and the 4, 0, 1. not to scale, it gives us a little tiny, if we don't go very far, it gives us a little tiny parallelogram. So when we look at the magnitude of the cross product, it's going to give us that area of that little parallelogram, and then we're going to add up all of them over all values of u and v. So let's find for this one, find the surface area if u goes from 0 to 1 and v goes from 0 to 2. So over that little sphere, square, rectangle. And then we know the magnitude is the square root of the sum of the squared, just the Pythagorean theorem. And so I get something like that. So the thing inside the square root, inside the double integral, the square root, is the area of one of these little pieces. And then we're adding up over all the little pieces. So here we can't still picture it, but what I'm going to do now is show that we can get this in terms of the original function of x, y, and z, and go back and look at the area in my first picture, the paraboloid. So this is our first formula. So any questions on this before I do it in general? Okay, so let me erase. So given a three-dimensional object, so z is a function of x and y, is kind of our symbol. We just let x and y be whatever you want. So we'll call them u and v, just designating that those are independent. And then z will be f of uv, so therefore there is our parameterization. So there's our u, our r. So the f of xy, z is equal to f of xy is the same as this r. They're given the same picture. Which is that we've introduced, in some sense, new variables. So I can do, in general, so I don't actually have to do the parameterization. I can say, well, what does this give us? So what is the derivative of this with respect to u? So obviously the first term, the u is 1. Derivative of v with respect to u is 0. And the third one is just whatever the derivative is with respect to u. And then derivative with respect to v. Derivative of u is 0. Derivative of v is 1. And the derivative of f with respect to v. And again, we want the cross product. Here I'll just give, although you'll double check me so I can try to keep it all in one piece. So the cross product of these is given by that. So I times that. I could actually also get, depending on how I'm doing it, the positive, positive, negative 1, but that's not going to matter. And because u and v are kind of artificial, let me put it down what it really is. X is equal to u and y is equal to v, and show that we get this formula if we have something in the more traditional form, z is equal to a function of x and y. So I do one of these examples and then show that sometimes we will have to use the parameterization. So any questions on how you get this formula? Okay, so let me erase. So here's a picture. So here's the general paraboloid, but we're looking at just the unit square and whatever that piece of it looks like on the paraboloid above that little unit square. So I can't draw very well, but it's part of the paraboloid. If we wanted to get the whole surface area above the xy plane, we would say that x squared plus y squared is less than or equal to 4. And then we'd probably use cylindrical coordinates. So according to the last formula, we just need the derivative. So the derivative of f, or in this case z, with respect to x is negative 2x. Derivative of the function with respect to y is negative 2y. And like most of these where we're looking at square roots of sums of squares, it's not going to be a nice integral. So I would just ask you to set up. And you can see that doesn't really matter which way I did the cross product, because if they were negatives, it would still be 1 plus 4x squared once I squared it out. Okay, so any questions on this? All right, so let me now do one where it's not quite as obvious how you would do this without doing parameterization. So let me erase this. Oh, sorry, question? Right, so this, in some ways that's, so I anticipated the question to ask, why do we parameterize? So let me look at one where we do parameterize. So this one we didn't have to. And now let's try one where it's not obvious how we would do it directly. So first, you can see this is kind of a made-up example because you don't need an integral to get this at all. So here I want to find the surface area of the open cylinder. X squared plus y squared is equal to 16. from 0 to 6, well, if I cut it and unrolled it, it's just a rectangle where the height is 6 and the length is the circumference, which is 2 pi r. R here is 4. So it's going to be 6 times 2 pi times 4. So in some ways we can do it without an integral, but in this one you can kind of see it. So the question is, going back to the last one, is we want to know what's the function. And you can see, well, we're kind of missing something here. We sort of have a function, but not really. So there isn't really a function of x and y. Okay. So someone said they can't really hear me, so let me go back and forth here a bit, see if it works. Can you hear me now? Okay. So there's not an obvious way how we would do this using the last formula because we don't have a function of x and y. Instead, what we're going to do is parameterize. And this one, pretty obviously, what we're going to want to do is use polar coordinates. And y, on the other hand, can be whatever you want. So we're going to do our x is equal to r cosine of theta, or u, whatever you want to call the variable, where r is 4. And z is equal to 4 sine theta. In some ways, it doesn't matter which way I do those. So either I can let x be cosine or z be cosine. Doesn't matter. And on the other hand, y is just itself. So therefore, our parameterization is that. And since we're doing the full cylinder, our margins are theta goes from 0 to 2 pi. It's all the way around. I don't know why it's doing that every once in a while. And y is from 0 to 6. So that last one is supposed to be 0 is less than or equal to y. It's less than or equal to 6. So we need our two partials. So our derivative with respect to theta is that. And our derivative with respect to y is that. And so I'll put this on the next one also, but trying to keep it so we have it here. So then the cross product is equal to, and again, I'll just do it. It's negative 4 cosine. This is not going to fit. Hold on. And then 0. And negative 4 sine. So I'll rewrite that in the next one. But any questions on this? So I'll bring that through. It's rewriting. And then use the more general formula. So theta goes from 0 to 2 pi, y goes from 0 to x, and then the square of the sum of the squares. And obviously, this is a simple one, so things actually do work out, because what do I get inside the square root? Obviously, what is sine squared plus cosine squared is 1. So I just get the 16 inside the square root, so I just get this whole thing simplifies to that. And since that's a constant, it's just the area, which is, as we did before, it's the 4 times the 6 times the 2 pi. So here's an example where the parameterization makes it so you can actually do the problem. It's hard to actually write the surface in terms of a function, in terms of x and y. So if you can, then you don't have to parameterize, but sometimes you have to parameterize to get what's going on. So any questions on this? As always, we'll have to do more examples. And also, I should remind you that this is not on the quiz, as is 2.8. 2.8 is also not on the quiz. Okay. So let me now do, in our regular classroom, would have been the typical thing, which is let me do the quick intro and see where we're going. So here's kind of our first one for today. So we're not really going to do this, as I said, kind of typical thing. Chapter 4 is looking at vector fields. So chapter 3 is looking at 2 and 3 dimensional spaces. The difference here is that when I look at a point, I'm not thinking of it as a point anymore. I'm now thinking of it as vectors. And so I'm just going to do 2 examples showing what I mean by that. So for example, a gravity field due to a point. So this is our function. But now each of these points, so if I put in a value of x and y, so for example, if I put in point x equals 1 and y equals 0, which gives me negative 1, 0, that is now a vector. And what's happening here, let's assume that the point mass is in the origin. When I put that in and get the negative 1, 0, so if I put in 1, 0, which I'm here, I get a vector that's pointing towards the point mass. And if I'm going to put one here, I get a vector that's pointing to the mass, and so on. And this is called a vector field because instead of points, we're thinking of them as vectors. And in this, I might want to know how much work does it take me to move along a path. So I'm here, I move along a path. How much work does it take me to do that? Well, the one I've drawn probably 0 because I'm perpendicular to the force, but you get the idea. And this is what's going to give us in chapter 4 what are called line integrals. So I want to see what happens if I move along a path where it's being affected by either a force or something similar. So that's the first thing we're going to use vector fields for, and that's what it represents. So it might represent how gravity is affecting stuff around it. So that's one. Any questions on this? We're not really doing it, of course, but any questions? Okay. Another example would be just the flow of a river. And we can either do this in 2 or 3 dimensions. So if I do 2-dimensional, so I'm looking at a cross section, then f of xy might be the velocity at that point xy. And here, what I might want to do is how much water is going through an imaginary surface. So the water can still go through, but I want to know at a cross section how much water is going through that space in a particular time period. And this is going to be later in chapter 4, is what are going to be called flux integrals. So then the 2 main things, which is we can think of a vector field as just a gravity field, which is at each point you have a vector that's showing which way it's being pulled, or a velocity field where at each point you're told what is the velocity at that point. And one will give us line integrals and one will give us what are called these flux integrals, which will be the last thing we do. All right, so let me stop there for tomorrow. Try the homework for 2.8. Start the homework for 3.11, but know that it's not on the quiz. So the most immediate thing is we have the quiz for Monday. So look at the review from last week and look at the mock quiz and check to see if you have any questions, and we can go over some of those tomorrow. So like last Thursday, and hopefully I'll get better as we go along, I'll stick around for a little bit. A little though, I almost forgot. From 1 to 3, I'm going to try office hours where I'm doing it through Zoom. As I said, if you click on my email, you should be able to go into it, and you don't have to come the whole time, kind of usual office hours. And in some ways, what I'm checking is, in some respects, that's nicer than this Collaborate Ultra. So hopefully at least a couple people will try it, because I'm going to check to see how well it works. And if it works well, I might switch, because Zoom has some nicer features than Collaborate Ultra. But you'll let me know. So now that's all it for the class. And as with last week, I will stick around for a few minutes if you have any more immediate questions. Otherwise, I will see you tomorrow. So let me know if you have any questions. I see a lot of people are doing it. Oh, someone asks, so for the video, you can either come back to, once I stop the recording, you can see it in Collaborate Ultra, but I'll also put it on my YouTube channel. So either or. Any other questions? so I'm going to stop recording.